In this presentation, we have talked about Breit-Wigner formula. Breit-Wigner derived a formula to describe the concept of resonance scattering cross-section. For that, SO scattering by an attractive squirrel potential was used. This is an attractive squirrel potential. The depth of the potential is minus V0. Suppose the nucleon is present inside the squirrel potential, the potential value is minus V0. If it is outside the squirrel potential, the value of potential is 0. Therefore, V of R equal to minus V0 or R greater than 0 less than A. Then V of R equal to 0 and R greater than A. That means outside the squirrel. The Schrodinger equation used to describe scattering by the squirrel potential is d square u of r by dr square plus 2 mu by h cross square e plus v0 minus l into l plus 1 by r square, and that is multiplied by u of r equal to 0. This is equation 1. For an S wave, the value of L is equal to 0. Then the above equation becomes d square u by dr square plus 2 mu by h cross square into e plus v0 into u equal to 0. Here the condition is r less than a, which means that the nucleon is present inside the squirrel potential. Then the same equation is reduced to another one form. d square u by dr square plus 2 mu by h cross square into e u equal to 0. Here the value of r is greater than a. That means outside the squirrel potential. This is equation 2. This is equation 3. Put 2 mu divided by h cross square into e plus v0 equal to k1 square and 2 mu e by h cross square is equal to k square. Now the equation 2 becomes d square u by dr square plus k1 square into u equal to 0. This is 4. And the equation 3 becomes d square u divided by dr square plus k square into u equal to 0. This is equation 5. Now we have to write the solutions. The solution of equation 4 is u of r equal to a sin k1 of r. Now the solution for equation 5 is u of r is equal to another constant b into sin kr plus del 0. If the nucleon comes out of the potential well, it suffers to a phase shift, that is delta 0 is the phase shift. This is equation 7. at r equal to a, at r equal to a, the wave function and its derivative are continuous. R equal to a means at the boundary, at this point, in this point. Now see equation 6 at r equal to a, that means u of a equal to a sin k1a, where u of a which is equal to b sin ka plus del 0. This is 8, this is 9. At r equal to a, the wave function and its derivative are continuous, which means that a sin k1a equal to b sin ka plus del 0. A sin k1a which is equal to b sin ka plus del 0. This is the meaning for continuity. Then at r equal to a, the wave function is continuous. See here, this is one wave function, this is another. These are all continuous, and its derivative are also continuous. Now make the differentiation of this. This is equation 10. A cos k1a into k1 is equal to b cos ka plus del 0 into k. This is equation 11. If you consider a wave function, that wave function and its derivative are continuous at the boundaries. See here, 10 by 11, equation 10 by equation 11 gives sin by cos is tan, a get cancelled, so 1 by k1 tan k1a which is equal to 1 by k, bb get cancelled, 1 by k tan ka plus del 0. From the above equation, tan ka plus del 0 which is equal to k by k1 tan k1a. This is equation number 12. Just cross multiply this, k by k1 tan k1a equal to tan ka plus del 0. But tan of ka plus del 0 which is equal to tan ka plus tan del 0 whole divided by 1 minus tan ka into tan del 0. Here the formula I have used is tan a plus b equal to tan a plus tan b divided by 1 minus tan a tan b. See, this is equation 13. So left hand sides are equal, so the right hand side should also equal. You may write tan ka plus tan del 0 divided by 1 minus tan ka tan del 0 which is equal to k by k1 tan k1a, k by k1 tan k1a, k by k1 tan k1a. Now this is modified as tan ka plus tan del 0 which is equal to k by k1 tan k1a into 1 minus tan Ka into tan del 0. This is equal to K by K1 tan K1A minus K by K1 tan K1A into tan Ka tan del 0. Here tan Ka plus tan del 0 is tan del 0 plus K by K1 tan K1A tan Ka tan del 0, which is equal to K by K1 tan K1A minus tan Ka. See this tan del 0 term is brought to the left hand side, so it is taking its positive sign, and this tan Ka is shifted to the right hand side, so this is taken its negative sign. K by K1 tan K1A minus tan Ka. This is taking its positive sign. From this, take tan del 0 outside. Put a square bracket. 1 plus K by K1 tan K1A into tan Ka equal to K by K1 tan K1A minus tan Ka. This is equation number 14. Now read out this statement. Suppose the potential is shallow, that is depth is low, and in the case of very low energy scattering, that is the Ka value is far lesser than 1. If K is small, tan Ka equal to Ka. The value of K by K1 is minimum. This value is minimum, and the factor in the square bracket on the left hand side is almost equal to unity. See, the terms present inside the square bracket is equal to 1. 1 plus K by K1 tan K1A tan Ka equal to 1. Here Ka is very small, tan Ka equal to Ka. Therefore K by K1 is also very low. So the terms available inside the square bracket should equal unity. Now the equation 14 becomes tan delta 0 equal to this K by K1. This is very low, so we may discard it. If Ka is very small, tan Ka equal to Ka. Then this equation is reduced as tan K1A minus Ka. The 14 takes this form. This factor, these are all equal to 1. This K by K1 is negligible. Tan K1A, if Ka is very small, tan Ka equal to Ka. If theta is very small, tan theta equal to theta. Then this is equal to, take Ka outside, tan K1A by Ka minus 1. This is the value of tan delta 0. Put this some number, this is equation number 15. Now, read out this statement. If the depth of the potential is gradually increased, at a particular stage K1A will go through pi by 2. If the depth of the potential is increased, this K1A is approaching the value of pi by 2. This is pi by 2. Tan pi by 2 is infinity. So the entire is treated as infinity. That means tan del 0 equal to infinity. Automatically the value of del 0 equal to pi by 2, because tan pi by 2 is infinity. Now read out this statement. If the depth of the potential is gradually increased at a particular stage, K1A will go through pi by 2. When K1A will go through pi by 2, tan del 0 tends to infinity. This means that the phase shift del 0 also goes through the angle pi by 2. Now the scattering cross section becomes sigma total is equal to 4 pi by k square, because the formula for sigma total is equal to 4 pi by k square summation over L equal to 0 to infinity 2L plus 1 sine square delta L. This is the formula for total scattering cross section. For an S wave, L equal to 0. Therefore, sigma total comma L equal to 0 is equal to 4 pi by k square sine square del 0. If del 0 is pi by 2, sine pi by 2 is 90. Therefore, total cross section is 4 pi by k square. This is the total scattering cross section. If there is a bound state and when the phase shift goes through 90 degrees, that is pi by 2, the cross section reaches the maximum value and is called resonance. This is the condition for resonance. Suppose the phase shift is 90 degree, the cross section reaches its maximum value. That means the area available for scattering is maximum. This condition is called resonance. We shall now investigate the nature of the cross section near resonance. For that, consider the resonant energy by E suffix R. The phase shift is a function of resonant energy. As the phase shift at resonance is pi by 2, sine del 0 of ER equal to 1. How do you say sine del 0 of ER equal to 1? Suppose the value of del 0 is pi by 2, sine 90 equal to 1, and cos del 0 of ER equal to 0. Del 0 is the function of resonance energy. Suppose del 0 phase shift is 90 degrees, sine 90 equal to 1, but cos 90 equal to 0. So sine del 0 of ER equal to 1, cos del 0 of ER equal to 0. Now we have to expand sine del 0 of E and cos del 0 of E near E equal to ER by Taylor series. We have sine del 0 of E, which is equal to sine del 0 of ER plus dou by dou E sine del 0 of E at E equal to ER into E minus ER. This is the expansion formula. Now we have to modify this. This is equal to sine del 0 of ER plus dou by dou E of sine del 0 E equal to cos del 0 of E. If you differentiate sine del 0, this is changed as cos del 0 E equal to ER. So this is ER into d del 0 of ER divided by d, entire is multiplied by E minus ER. Sine del 0, then differentiation of sine del 0 is cos del 0 E equal to ER. Then we have to differentiate del 0, that is d del 0 divided by d. Here del 0 is a function of E equal to ER into E minus ER. We know that sine del 0 of E are equal to 1. This is unity. So this is almost equal to 1. Cos del 0 of E r is 0. 0 into anything? 0. Then sine del 0 of E equal to 1. Put some number for this equation. This is equation number 16. Sine del 0 of E equal to 1. This is 16. Now we have to expand the value of cos del 0 of E. Cos del 0 of E equal to cos del 0 of ER plus dou by dou E of cos del 0 of E at E equal to ER into E minus ER. This is cos del 0 of ER. Differentiation of cos del 0 is minus sine del 0 of ER. Minus sine del 0 of E, here E equal to ER, into d del 0 of ER divided by d. Entire is multiplied by E minus ER. Now we know the values. This is 0. Cos del 0 of ER is 0. Sine del 0 of ER is 1. So this is modified as cos del 0 of E, which is equal to minus of d del 0 of ER divided by d into E minus ER. Say this is 17. Now put d del 0 of ER by d equal to 2 divided by level width. Now cos del 0 of E, which is equal to minus 2 divided by level width into E minus ER. This is equation number 18. Now we have to write the value of f of theta, scattering amplitude. The value of scattering amplitude f of theta comma E, which is equal to 1 by k summation over L equal to 0 to infinity 2L plus 1 e power I delta L sin delta L PL of cos theta. This is the general formula for scattering amplitude. Say this is equation number 19. Now for an S wave, L equal to 0 and 1 by k is very small, will not be taken in our account. Therefore f of theta comma E becomes, if you put L equal to 0, this is 1, this 1 by k is discarded, e power I del 0 into sin del 0. P0 of cos theta is 1. This is the value of f of theta comma E. See, this is equation 20. Then this is further modified as f of theta comma E, which is equal to sin del 0 of E divided by e power minus I del 0 of E. This is equal to sine del 0 of E divided by cos del 0 of E minus I sine del 0 of E. See, this is 21. E power I theta equal to cos theta plus I sin theta. If you put e power minus I theta, that is equal to cos theta minus I sin theta. Using this, we have expanded this. E power minus I theta equal to cos theta minus I sin theta. Now, f of theta comma E, which is equal to sine del 0 of E equal to 1. Already we have proved this. Sine del 0 of E equal to 1. This is 1 divided by cos del 0 of E equal to minus 2 divided by level width into E minus CR. This is minus 2 divided by level width E minus ER minus I into sine del 0 of E is 1. So this is the value of f of theta comma E. Now this is modified as minus level width by 2 whole divided by E minus ER plus I into level width by 2. This is 23. This is the value of f of theta comma E. See here, just I have multiplied each and every terms by minus level width by 2. If I multiply this by minus level width by 2, level width get cancelled, 2 get cancelled, so E minus ER with a positive sign. Here plus I into level width by 2. Now the total scattering cross section for an S wave, sigma total comma 0, here L equal to 0 denotes the S wave, 4 pi by k square sin square delta 0. This is the total scattering cross section. In general, for an S wave, the total scattering cross section is 4 pi by k square sin square del 0 for an S wave. Now, we have to express sin square del 0 in terms of absolute square of f of theta comma E. See, f of theta comma E equal to 1 by k e power I delta L, then 2L plus 1 sin delta L PL cos theta. This is the value of f of theta comma E. For an S wave, L equal to 0, f of theta comma E, which is equal to 1 by k e power I del 0. Here L equal to 0 means sin del 0. P 0 of cos theta is 1. As we pointed out earlier, the contribution ended by 1 by k is very small. Therefore, f of theta comma E equal to e power I del 0 into sin del 0. Now, absolute square of f of theta comma E for an S wave equal to f star theta comma E into f of theta comma E. F star means e power minus I del 0 into sin del 0. Then f of theta comma e power I del 0 into sin del 0, which is equal to sin square del 0. So in the case of total scattering cross section, instead of sine square del 0, we can put absolute square of this f of theta comma e. Therefore, sigma total equal to 4 pi by k square into absolute square of theta comma e. This is equal to 4 pi by k square. Then absolute square of f of theta comma e is, take the square of this, level width square by 4. This negative sign is changed as positive. Level width square by 4 divided by E minus ER whole square. Now here the term is, see here, I into gamma by 2. Here, if you take the complex conjugate, if you make the complex conjugate I star, this is actually complex conjugate of this term is I into gamma by 2 into minus I into gamma by 2. I into I square, minus 1, minus into minus, plus. So this is plus gamma square by 4. Because we are taking complex conjugate of this term, absolute square of f of theta comma e, not mere square. If it is mere squared, this I square is minus 1, so minus gamma square by 4 we can arrive. But we are taking the complex conjugate of this entire absolute square of f of theta comma e. That means this term into complex conjugate, minus gamma by 2 into minus gamma by 2 plus gamma square by 4. E minus r into E minus r, that is E minus ER whole square. Here I into gamma by 2 into minus I into gamma by 2. Therefore, plus gamma square by 4. Then the total scattering cross section equal to 4 pi by k square into gamma square by 4 whole divided by E minus ER whole square plus this gamma square by 4. This is our level width. This is called Breit-Wigner formula. Here this is our level width. This level width, which talks about energy distribution. We talk about this level width while studying our compound nucleus. This is our Breit-Wigner formula.